Good morning, fellow mathematicians, welcome back to another video. I haven't posted in a while. That's going to be the compensation for you. It's going to be quite a long video today. We're going to talk about this integral right here, the integral from 0 to the ln of x of a maximum function of 1 and y dy. You might be wondering what a maximum function is. Well, this function just spits out the bigger of a bunch of numbers. For example, the maximum of -1 and 3 is just 3. So it spits out 3 on the other side. And we can bring this right here into an algebraic expression. So give me a little time to show you a geometric interpretation of this function right here. So suppose we are walking on the real number line here, and there are some points A and B, and B is going to be the bigger of those two numbers. So how can we land at the bigger number B? So at first we could walk right into the middle of those two numbers. How can we land in the middle of two numbers? Well, we could take the arithmetic mean of those two numbers. So we would end up with a plus b over 2. So what else is left? Well, we have to walk half the distance between those two numbers to the right. That means we have to add half the distance of those two numbers to this expression right here. So what's half the distance? Well, we could use, for example, the taxicab metric on this one. That would be d of a and b will be defined as the absolute value of a minus b. And since we want to walk half the distance to the right, we want to add the absolute value of a minus b over 2 to this expression. And this right here holds for all real numbers. So we can do this and we can plug this into here and then we can move on. Okay, so what do we have at first? That's the integral from 0 to ln of x of 1 plus y plus the absolute value of 1 minus y over 2 dy. Okay, that's the first part. And in case you might be wondering, x is in R, so it's element of the real numbers. So let's say x is element of the real numbers. Just to clarify that. This fact is quite a neat one, we need it later on. Okay, we can use the linearity of the integral now to split this one up, and well, two parts are quite easy to integrate, the last one is quite hard to integrate. So let's go ahead. At first that's the integral from 0 to ln of x of 1/2 dy. Then we can add the integral of y over 2 dy, and in the end we just have this last part. I'm bringing this 1/2 to the front, so that's 1/2 times the integral from 0 to ln of x of the absolute value of 1 minus y dy. Okay, so like I said before, those two are quite easy to integrate. We know how to do that. At first we get y over 2 from 0 to ln of x plus y squared over 4 from 0 to ln of x, and we are going to call this last part right here I. Let's just call it I, plus I. Okay, so what we end up with is, if we plug in 0 into those functions, those become just 0, so those cancel out, and we end up with the ln of x over 2 plus ln squared of x over 2 plus I. And now we have to talk about I. Be aware, my boys, we are dealing with a Sharpy boy now. That means we can just integrate however we want. So let me show you what a Sharpy boy looks like. The graph of this function, absolute value of 1 minus y, looks as follows. Here's the point 1 on the x-line, on the x-axis, and well, that's how the graph looks like. But the thing is, we can't define a slope in this point right here, 1 and 0. And that means it's not really defined. It's, well, not continuous. We are dealing with a piecewise continuous function. So we have to make some preparations to get around this point. And we can take a look at two cases. Either we are not even reaching this point, that means we are integrating from 0 to the ln of x when the ln of x is less than 1, because if we would reach 1, that would mean we get the absolute value of 0, and we don't want that. We don't want that, that's not defined, we can't really integrate that. And the other case is we are using the ln of x greater than 1, but we have to get around this point 1. That means we have to take the principal value of the integral Okay, so that means we are starting off with the first case when the n of x is less than 1. That's the easier case. So, wie soll's Jens here? No. Okay, let's start off with the first case. When the n of x is less than 1, which means equivalently that x is less than e. Okay, that's the first case. At first we want to introduce a u substitution. So, let some arbitrary u equal to 1 minus y. That means that du is equal to minus dy. We can plug those new values in. That means that I is now just 1/2 times the integral from, if we plug in 0 into here, we would end up with a 1, u equals to 1, and if we plug in ln x, that's 1 minus ln x. So we can do this, so from 1 to 1 minus ln of x, and now we get the absolute value of u times minus du. Okay, we can bring this minus to the front, we can distribute it into the integral and change the order of integration. So that's what we can do at first. So we end up with 1/2 times the integral from 1 minus ln of x to 1 of the absolute value of u du. And you might be wondering, how can we integrate the absolute value of u? Well, the good thing is, we are moving along a non-zero set, so we can actually integrate this by doing some algebraic manipulation and integration by parts. So at first, let's rewrite this. So that's 1/2 times the integral, upper and lower bound, of u over u times the absolute value of u du. And I hope you agree with me that we can do this, because that's u over u, that's just a 1, and we can multiply something by 1 and it won't change anything. So that's a good thing. And here's some trivia for you guys. There's a function that's called the sine function. And sine of u is defined, but only on non-zero sets, as absolute value of u over u. And that's exactly that. Just trust me on this one. I'm going to show you that this one right here has a primitive in a different video, at least on non-zero sets. So what we end up with is just 1/2 times the integral of u times the sine of u du. And the sine of function just spits out the sine of some number. So that means the sine of -3 would be -1. So that's what it does. And now we want to use integration by parts. We need something to differentiate and something to integrate plus minus. Okay, let's differentiate u, that goes to 1. And the sine of u on non-zero sets can be integrated to the absolute value of u. That's nice. Okay, so what we have now is just 1/2, don't forget the 1/2. 1/2 times u times the absolute value of u. So we have to multiply those together and we have to subtract this integral right here. And minus 1/2 times the integral. Oh, don't forget the upper and lower bound. 1 minus ln x to 1. And now this integral from 1 minus ln of x to 1 of absolute value of u du. And you might be noticing that this part right here is just our I. So what we can do, we can add I on both sides. That means we get 2I is equal to this expression right here, and then we can divide by 2, and that's the answer for our integral. So that's great. So what we can conclude is that I is equal to 1 over 4 times the absolute value of u times u of 1 minus ln x to 1. And we can plug those values in. So what we end up with finally is just 1 over 4 times, okay, that's absolute value of 1 is just 1, so that's just 1 over 4. So that's 1 minus, and then, so what do we have? That's 1 minus ln of x times the absolute value of 1 minus ln of x. So that's the solution to our integral. We can distribute that and then we're done. Okay, so that's great. But this is just the solution to our I. So to get to the real integral, we have to add this first part of ln x over 2 and stuff like this to it. Let me write it on here and then we will solve for it. I'm back. Okay, so I called our original integral j, just to make things clear. Okay, so that was the original expression and I plugged everything in. And now we can do some arguing to get rid of this absolute value right here. Okay, so I hope you guys remember that the ln of x is supposed to be less than 1 in case 1. That means that 1 minus something less than 1 would be a positive value. So that's great. So the absolute value of some positive value is just the value itself. So we are just getting rid of it. So let me rewrite this. That's that. And that's the same expression. So that's just 1 minus ln x squared. And we can solve this. So that's del n of x over 2 plus ln squared of x over 4 plus 1 over 4 and then minus. Okay, the first part is just 1 over 4. So that's nice. We are getting rid of that. And then positive ln squared of x over 4. And also we get negative and negative. Oh no, this is negative. Hello? Someone just came in as always. Okay, and the last part is just positive ln of x over 2. So that's great. And we have a lot of things that we cancel out. So this we cancel out, this we cancel out, this and that. Okay, and what we end up with is just 2 times ln of x over 2, and that's just del n of x. So that's probably the worst way to evaluate the natural log of x. And now we are moving on with the next part. So this next part, my boys, is going to be a little bit more complicated because, like I said before, we want to take the principal value of this integral right here. So I'm just going to give you a little idea what a principal value is. We can't integrate over this undefined spot, over the singularity. So that means we have to find a way around it, a little detour. So that means we just want to approach it from one side. So that means we are going to go to the ln of e minus epsilon. So we are approaching it from the left to the right. And then we are just avoiding the spot when x would hit e, because that's the spot where our natural log would become 1. We don't want that. And then we are moving on from the ln of e plus epsilon to our desired ln of x. So we are just going to avoid this spot ln of e by a little margin, by a little piece of number. So that's what we are going to do. That's the basic idea behind it. So what does it mean? The principal value of our integral I. What is that? Well, that's just 1/2 times the integral from 0 to the ln of e minus epsilon. So that's the first part we want to approach, of the absolute value of 1 minus y dy. And now we are adding our second part, plus 1/2 times the integral from ln of e plus epsilon to the ln of x. And that's case 2. I forgot to erase that. Of the absolute value of 1 minus y dy. And now we can do it like before. We can introduce a u substitution, and let's see what you get. So that's now 1/2 times the integral form. If we plug in 0, that's just 1 once again, and that's 1 minus ln of e minus epsilon. I'm doing the substitution in my head now. Don't want to write it again. Of the absolute value of u times minus du. And then positive 1 over 2 times the integral from 1 minus ln e plus epsilon to 1 minus ln of x of the absolute value of u minus du. Okay, we can bring this minus to the outside and change the order of integration. Let me do this real quick. This is now just 1/2 times the integral from 1 minus ln of e minus epsilon to 1 of the absolute value of u du, and then positive 1 over 2 the integral from 1 minus ln of x to 1 minus ln e plus epsilon of the absolute value of u du. I hope that's not too boring. It's a lot of writing this time. And luckily we are moving along a non-zero set because we are avoiding ln of e, so that means we can't hit the spot 1. So we can actually integrate those absolute values once again, so that's absolutely astonishing. That's fucking amazing, my boys. So what we end up with is just, so what was it? That's 1 over 4 times the absolute value of u times u from 1 minus ln e minus epsilon to 1, and then positive 1 over 4 times the absolute value of u times u from 1 minus ln of x to 1 minus ln e plus epsilon. And we can plug in those upper and lower bounds and see what we get on the next chalkboard. So I plugged everything in and I ran out of space on this column right here, so I have to continue here. And now we have to argue a little bit once before to get rid of the absolute values. And I want you guys to remember a certain identity that we can use on absolute values. So if you get the absolute value of a minus b, for example, or a plus b, it doesn't matter, we can factor out a minus 1. So that's minus 1 times b minus a. So we would indeed change the order of this right here. And then we can use the multiplicativity, what a weird word, of the absolute value to transform it into the absolute value of minus 1 times the absolute value of this chunk right here. And well, absolute value of minus 1 is just 1. So what we end up with is b minus a. So that's abelian right here. We can change the order of subtraction. And we can do this on those terms here. So how can we argue? Well, ln of e minus epsilon is strictly less than 1. That means this value right here in this absolute value is just positive. That means our absolute value will just vanish. Okay. Now we get the ln of e plus epsilon. Well, that's strictly greater than 1. So this right here would be negative. So we can factor out a minus 1 and change the order. Let me write everything here. Okay, so we just argued and we can change the order of addition right there. So we end up with ln of e plus epsilon minus 1. Okay, and for the last part, well, same thing here, ln x. That's our second case, is strictly greater than 1. That means that's negative, so we can change the order by factoring out a minus 1. So that's positive 1/4 times 1 minus ln of x. And then ln of x minus 1. And now we can distribute everything into everything and see what we get. Now let's see what we would end up with when we distribute everything into everything. We are reaching the end, my boys. So this is now ln of x over 2, positive ln squared of x over 4. And also, I'm terribly sorry, I made a little sign mistake right here. There was supposed to be a minus there. I got rid of that. And then positive 1 over 4. Next thing, minus 1 over 4, and then positive ln e minus epsilon over 2, and negative ln squared e minus epsilon over 4. So for the next part, it's kind of the binomial formula. Just factor out a minus 1, and then this will get the job done. So that's minus 1 over 4, and then positive ln e plus epsilon over 2, and negative ln squared e plus epsilon over 4. And for the last part, same spiel once again, minus positive 1 over 4 in this case, and then negative ln of x over 2, and positive ln squared of x over 4. And let's see what we can conclude at first. So this will cancel out, this will cancel out, this will cancel out, and this will cancel out. And also this will cancel out, and this will cancel out, and we can bring those two together to the ln squared of x over 2. And we can, well, yeah. Let's see what we get at first. So this is now ln squared of x over 2. So we got rid of this and this. So next thing, we can factor out a 1/2 on this one. So this is positive 1/2 ln e minus epsilon, and then positive ln e plus epsilon. Okay, and we can factor out 1 over 4 on those two terms. So that's negative 1 over 4, and this is ln squared e minus epsilon, positive ln squared e plus epsilon. Okay, great. So that's basically our solution. You can bring together those ln's, but let's see what would happen if we let the epsilon approach 0. That would mean that this is just ln of e, so that's 1, and this is also a 1 right here. So this right here would become just 2 times 1/2, so that's 1. So the limit as epsilon approaches 0, what would we end up with? So that's ln squared of x over 2. And the next part, that's positive 1. And what would happen here? Well, that's ln squared of e, so that's a 1, and that's also a 1, so that's 2, and this is minus 1/2 all in all. So minus 1/2, and we end up with ln squared of x over 2 plus 1/2. So that would be our final answer. No, this is actually our final answer, but if we let epsilon approach 0, that would be our final answer if we would just ignore this principal value stuff. So that's it. This was like the 8th time recording this video. Because it's such a long one, I failed so miserably all the time, and also headaches are killing me in the last month and I can't get rid of them. I'm having headaches every day and it's just so annoying. I can't concentrate properly and also I have exams to do and yeah, stuff like this. So I'm terribly sorry. I hope this video was kind of okay. If you did enjoy this video, please like and subscribe, recommend me if you like, support me on Patreon if you want, and up until the next video, have a flammable day. See ya.